to give his talk on well, machine learning inference through simulation. So up to you, Cosma, and thank you again for talking today. Cosma, are you here?
Yes. Can people hear me?
Yes, great.
Terrific. All right, so thank you everyone for being here. Thank you to the organizers for inviting me. I'm very pleased to have this audience be the first time I'm actually presenting this work, which has sort of been my baby over the last 2 years since I had a brainstorm when we were all being sent home. And so I'm very eager to hear what an audience like this, which knows far more than anyone else about simulation-based inference makes of this, and hopefully you will either make this much better or tear it to pieces, and I will not have to waste any more time on it. So with that said, I want to begin with an apology. Over the last 2 days, one of the keys on my laptop has started dying. And so I am sure that there are horribly embarrassing typos somewhere in these slides. It is thermodynamically inevitable at this point. I apologize. And of course, it would be the S key in the talk about simulation. There's just, there's no way to Olipo my way out of this. So I have sat, like all of us, through far too many Zoom talks, and so I've decided that I need to begin with a summary. And so this is what I want you to take away from this talk, so you get it first. The first is point, which you guys all know, is that there's a common pattern to a lot of simulation-based inference, which is we have this machine which spits out things which look kind of data-like, and there are some knobs on it called parameters, and we adjust the knobs until the simulation output looks like the data, but we don't want it to match the data exactly. We think the data is random. Matching the data exactly would be silly in that case. We want it to match certain aspects or certain features of the data. And when we try and actually do one of these projects in practice, we end up spending a lot of time, or at least this is my experience, we end up spending a lot of time trying to decide what aspects of the data are actually important to match for our model versus which ones we can write off as noise and accident and irreproducible results. And our folklore says that you get much better estimation or much more powerful tests if you have a good choice of features to look at, whereas if you make bad choices, stupid choices, you waste a lot of time and you don't use your data efficiently. What this work is about trying to take this second step of deciding what to do and saying, I think there are at least some situations where we can automate that or largely automate that. And the idea is that if we take a set of basis functions, and those basis functions are in certain senses rich enough and smooth enough, then we can pick functions from that set at random, and all we have to do is match the values of those randomly chosen functions, those random features of the data. And matching a limited number of random features is actually going to be enough to give us consistent estimates. And while I certainly don't have a proof of this, I have some numerical evidence that at least sometimes it's actually a reasonably efficient estimate. And the thing I really hope to convince you of is that if the models are nice, if they form a manifold in a certain sense, so a smooth geometric structure in the space of probability distributions, and you've got a d-dimensional manifold.
Can you repeat the last sentence, because at least for me you were cut.
Sure. What I'm going to try to show you is that it's not just that we can match random functions at randomly chosen features and get consistent estimates. I have some evidence that at least some of the time, those give us fairly efficient estimates. I don't have a proof of that or any idea of how general that phenomenon is, but I would really like to know. And I want to also try and convince you that if the models have have a nice geometric structure, if they are smooth in a certain sense, and you've got D parameters there, so they form a D-dimensional manifold, the number of random features we need is about 2D plus 1. And that's in the worst case. Okay, so it's not just that enough random functions are going to give us consistent estimates. It's a very limited number of random functions will actually give us consistent estimates. So this is the message I want to get through. And now we can go back to doing whatever it is that you do that we all do in Zoom meetings. But if you do want to continue focusing on this rather than multitasking, the agenda is, first I want to convince you there's a problem that needs to be solved here, which is how do we pick the features we try and match in simulation-based inference. I want to sketch out the solution. I want to show you some pictures, which I'm going to claim indicate that this thing I'm purporting as a solution will actually do something good for us. And I want to talk about what the future directions are for this. And hopefully then that'll be 45 minutes and we can, and I will be then happy to take questions. All right, so let's just synchronize ourselves about what usually goes on when we're doing simulation-based inference. I realize this is the ABC seminar, but I have this frequentist lizard brain, so I'm just going to talk about the frequentist way of doing this. We could talk about the ABC approach instead. So this begins when someone shows up at our office door and they're holding a data set. And so it's some big thing with n observations in it. And they also, because they are a scientist and they have ideas, they have a model. This model says that data X is actually a random variable, and there is some distribution which is parameterized by our old friend theta. And in this situation, theta has got D dimensions. And because they are a scientist, they have not made it so that you can do any sort of good statistics on it, but it is an actual generative model. So if you feed in random numbers or pseudo-random numbers, you can simulate it at any value of theta you like, and we'll get some simulation output, which I'm going to write with a tilde x, and I've got theta as an argument, indicating that if we change the parameters, we would get different simulation output, even if we fed in the same pseudo-random numbers into the stochastic model. But as I said, they have not been thoughtful enough to make this something with a tractable likelihood function. There are thresholds and latent variables and sensitive dependence on initial conditions and everything else, which makes calculating the likelihood of the data intractable. And that means we can't maximize it. It means we can't do the Bayes thing of taking the likelihood and corrupting it with our prejudices. We have to do something else. And canonically, what we do in simulation-based inference is we're going to pick some features or statistics, so just functions of the data. We're going to pick a certain number of them. I'm going to let that number be k. And then we're going to hope some things happen or postulate that some things happen. One is that the expectation of these features under the distribution, and I'll just use the abbreviated notation, what some people sometimes call Definetti notation, where you stick the measure times the function and you say that's the expectation value, right? That should converge as we get more, as n gets larger and larger. So these functions are chosen in such a way that their expectation values are tending towards a limit, which just depends on the parameters. So n, notice over here, is dropping out. And the other thing we want to have happen is that if we take one of these features and we calculate them on our actual random data, that should converge in probability, at least, on the same limit. So there should be a law of large numbers or ergodic theorem, if that's what you want to call it, for these features. And so they should be, we should have convergence on some limiting deterministic function. If you are an indirect inference person, you call this the binding function. And the values of these features calculated on the random data should converge in probability to that binding function. Okay. And then we also are going to hope that this binding function, this phi, is invertible. Okay. So there is a way of tracking back from the values of these, the limiting values of these features to the underlying parameters. So how do we use this to do inference? Well, the ideal would be that we would observe one infinitely large sample, one infinite realization from the process at the true parameter value. And then we would say, okay, we'll calculate the features from that infinite realization. Phi inverse exists, so we can stick it into that, and that would give us back the parameters exactly. Okay. Now the problem is we have finite data rather than infinite data. So you could imagine saying, well, we'll calculate those features on our finite but random data, and we'll stick it into this inverse binding function. And that will give us an estimate of theta, and it won't be exactly right because there's some noise in here. But that's not really feasible because we don't know this inverse function. These models are things we have to simulate. They're totally intractable. There is no way we are calculating this inverse binding function. And anyway, there's some random noise in here and we're ignoring that. So what you could do instead is you could say, all right, I will say what's the best match, what's the closest approach to the actual value of the features from the binding function. So I will look over all values of the parameters. I will adjust the parameters until the limiting value of the features matches the value I calculate on the data as closely as possible. And I've just written this as the squared distance, but if you want any other positive definite quadratic form because you want to compensate for variance, et cetera, that's fine. It's the same idea. Of course, we don't know the limiting binding function. We don't know the limiting values of the features as functions of the parameters. So you say, okay, fine, we'll stick in the actual expectation at some finite n. And even that we don't know because these models are totally intractable and we can't actually calculate any expectations in closed form. So we'll say Monte Carlo is our friend. We will just simulate from a parameter value S times. S is set by our patients. We will calculate the feature on each run of the simulation, and we'll average that. And that's going to be approximately the expectation value. And so now we finally have something where every term in this is an object we can calculate. And this is a feasible estimate. This is our simulation-based estimate. And you can see how as we let n get larger and larger, if these things I called hopes on the previous slide are true, this is actually going to converge on the estimate we would want, which is the infeasible one which was what we would do if we could work out everything exactly. So we have a feasible simulation-based estimator, and because we're only doing a limited amount of Monte Carlo, there's an extra factor in the variance. It's a 1 + 1 over S, where S is the number of simulations we do per parameter value. But this is something we can make as small as we like, just by being more patient or having cheaper computing time. Okay, so this is the usual pattern. What can we say about this? One thing is we're going to need at least as many features as there are parameters we're trying to estimate, because we want there to be an inverse, right? We want there to be an inverse function. You could imagine that there would be very discontinuous space filling curves, which would map invertibly from one 2 dimensions to 1 or something, we don't want to use discontinuous space filling curves. That's sort of a mathematical aside. We really want this inverse function to be smooth. And the reason is that if we have, we know there's going to be some noise in our features, they're stochastic. So if we have a little bit of noise in the features, we would like that to translate back into a limited amount of noise in our estimate. And so that's essentially saying this inverse binding function should be a smooth function. Depending on the flavor of simulation-based inference we do, we're talking about different choices of these features. The ancestors back in the day said, well, we'll just use moments, we'll calculate moments by simulation, or we will use generalized moments. So we have the method of generalized simulated moments. Again, this is we're just saying that's a particular choice of feature that we're trying to match. Indirect inference is this wonderful idea that we will come up with another model, which we don't believe, and we will use the parameters in that other model as our features. Really, we're using point estimates of the parameters in that other model as our features. And it's a very nice idea, but then you have to choose the auxiliary model. And of course, for ABC, we do something very similar in the choice of summary statistics. I know everyone here is very familiar with the pain that can cause, and probably more familiar than I am with some of the techniques people have developed for trying to automate choice among a limited set of summary statistics for ABC. One of the things we want in general is we would like the derivatives of these features, these limiting features with respect to the parameters, to be large. And you need to say that a little carefully, because you don't want to just multiply the features by 10 and say that it's now more sensitive. If you just did that, there'd be other canceling factors. But the basic point we want is that if you make a little change in the parameter, that should ideally translate into a big, easily detected change in the feature. And the more sensitive the features are to the underlying parameters, the more efficient these estimates will be, the smaller the asymptotic variance of these estimators will be. Now, that's the usual pattern. As I said, we're all pretty familiar with it here. The thing I want to emphasize is that trying to come up with those features is usually a problem. Ideally, you would use a sufficient statistic. If your model is tractable enough that there is a sufficient statistic that you can find, it is probably not something where you need to do simulation-based inference. It is a well-behaved exponential family, and there's no need for any of this. So that, again, that is a mathematical ideal rather than I think a genuine consideration. What you want to avoid are features which don't change very much as you change the underlying parameters in the generative model. If those derivatives were 0, you would not be getting anything from doing this. So that's the situation we want to avoid. What we want to actually do, after thinking about it, it seems that there are a very limited set of sources for where we come up with these features. One of them is tradition. And I do mean tradition. It's stuff like you copy from the last paper you did, because it was probably a similar model. You copy from your teachers. You have a vague memory of another paper. Or if you're a student, you Google it because and that takes you to Stack Overflow or something like that. So that's fine. Tradition is a good starting point. After tradition, you need to apply analogy, because your problem is almost certainly not exactly the same as the problem you've known in the tradition. The model is different, or the data is different, or something about the measurement process is different. And so then you just make stuff up, but you hope it resembles the stuff from the tradition. And sometimes that making stuff up is guided by some insight into the underlying model. So, you say, well, we're modeling a financial market and we know there are heavy tails in price movements. So let's estimate a Pareto exponent, even though we know the actual distribution is not a Pareto, because that'll at least tell us something about how heavy the tails are. And so we'll throw that in as part of our auxiliary model, or we'll throw that in as a feature. Or say we really care about the dynamics here, and the easiest model for a dynamical model for us to estimate is linear autoregression. So let's estimate the coefficients of the linear autoregression, and let's call those features, and we'll pick some number of them. Why not? How much time do we have? And there's also the approach of just saying, I'm going to come up with all kinds of things, and I'm going to put them all into a big pile of features, and I'm going to hope that some of them are informative, and I'm going to hope that I'm doing this in my tuning, my adjustment, in a way where the informative features actually win out. And there's a very lovely paper by Simon Wood from a while ago now, where he sort of gives some justification for that approach, which I think should be a little better known than it is. But the final ingredient in deciding what features to use is massive amounts of trial and error. You spend a lot of time saying, I'm going to simulate from my model. I'm going to see if my estimator can recover the parameters in my own simulation output. And when it doesn't work, you say, well, am I using the right optimization routine? This optimization routine doesn't seem too bad. Probably the problem is in features. What feature should I add? What feature should I remove? Et cetera, et cetera. How much time do I want to spend on this? And again, just in my experience of doing this in applied work, this is where most of the human time comes in. Not necessarily most of the computer time, but human time is, or should be, much more valuable than computing time. And so this is the part where I think we would be able to use simulation-based inference much more readily if we didn't have to think so hard about it. Or if at least if the thinking could be much more straightforward and much less floundering. So what would be nice, what would be a good solution here, would be a way of picking features automatically, without having to really understand the model, because understanding models is hard. And it would be terrific if it led to small variant, statistically efficient estimates. I'm not going to worry about computation time here. And it would be nice if we didn't have to use too many features, because calculating lots of things is a bit of a pain. So here's what I'd like to propose that we do. We've got our model. It's got D parameters, and the parameter space is a manifold. So it's a nice, smooth geometric structure. So if you have a sequence of parameter values which are converging on some limit, in that along whatever the geometry of that manifold is, then the distributions converge. Corresponding distributions converge. So this is what the information geometry people think about statistical manifold assumption. And so then I'm going to say, okay, we've got a d-dimensional manifold. It looks like we've got this huge n-dimensional distribution, but really there are only d degrees of freedom buried inside that. So what we should do is we should take not D features, but 2D plus 1 for reasons I will explain. And we're going to pick 2D plus 1 random functions. They should be continuous, they should be bounded, they should be a nice basis for the function space. So there's going to be some nice set of basis functions. We're going to pick 2D plus 1 of them, and those are going to be our features. And we're going to set a certain number of simulations per parameter value. And then what we're going to do is we're going to say, okay, what is the value of those randomly chosen features on our data? And we have picked them without looking at the data. We've basically picked them without looking at the model, other than knowing what the sample space is. And then we're going to say for each value of theta, we're considering, we're going to simulate the model S times at that value of theta. We're going to calculate the features. We're going to average. So this is going to be our approximation to the expected value of those random features. And we're going to minimize the distance. Okay, so we're going to minimize the squared distance between the actual value of the random features on the data and its expectation done by simulation on the model. Okay. So clearly I need to say something about why this should work, which will mean a little bit about what is this rich enough set of functions, and where does this magic 2D plus 1 come from? So the function set comes from thinking about this idea in machine learning of what they call random feature machines, or sometimes random kitchen sinks. And the starting point there is to say, look, we've got some class of functions which are a good basis for a very large function space. So the classic example, and what I'll use in my demos, is just the Fourier basis. So sines and cosines, or cosines with that you can build up really complicated functions out of combinations of sines and cosines. They're not unique for that, but they're a good starting point. The kind of function we'd like integral mixture of. So in the Fourier case, you should think about a function which has a nice, well-behaved Fourier transform, which you can invert to recover the original function. And we're going to make up some distribution over the index, the thing I've written omega, of these functions, of these basis functions. So we're going to pick the basis functions independently, identically distributed from some fixed distribution. And we're just going to pick a limited number of them. So then we're going to consider linear combinations of those randomly chosen basis functions. So you should think, we've got, say, a Gaussian distribution over frequencies. We are going to pick k cosines with those Gaussianly chosen frequencies. And we're going to consider that linear combination of k cosines. So the remarkable result, and a lot of the work here goes back to Ali Rahimi and Benjamin Recht about 14 years ago now. It says, actually, this gives you an order 1 over root k approximation to any function you like in this big integral class. And that's an approximation in L2 under any distribution on X, and it's even an approximation in L infinity on bounded sets. So you can get a very close approximation, order 1 over root k, just by picking random basis functions from some fixed distribution. And very remarkably, the dimension of X doesn't show up in any of the approximation results. So, if you have some function with a nice Fourier transform, you need to approximate it. You can do that with a very limited number of Fourier basis functions chosen at random from, say, a Gaussian distribution over frequencies. So even if you do not pay any attention to the stuff I'll say about 2D plus 1, I think this is something which people in our world of simulation-based inference should use more often. People in ML have been exploiting this for 10, 15 years, and there are some really remarkable results in a lot of applications, including stuff like random function approximations to PDEs and so forth. So this is a very brief mention of the motivation for why random functions chosen from a nice rich basis class. But if you take that seriously, that order need, saying if you want a good approximation, the number blows up rapidly for a small approximation. As I said, we definitely need at least as many functions as parameters we're trying to estimate, but it would be nice if we could use, if the number of features we needed was on the order of the number of parameters we were trying to estimate. And so this is where there's this result about manifolds that comes in. This is something called the Whitney embedding theorem from the 30s. And the way it works is like this. So we have our favorite manifold, it's got d dimensions, and we're going to think about maps from that manifold to k-dimensional Euclidean space. And we're going to insist that each coordinate going forward is continuous and continuously differentiable. And we're going to, but we've got this, vector valued map. So we're going to say that's an embedding if the inverse function also exists on the image of the manifold and is also continuously differentiable on the image of the manifold. So then this function from the manifold to Rk, well, that'll be a diffeomorphism. It'll be a one-to-one invertible mapping, which preserves the differential structures. So Whitney has this wonderful theorem, which says that once you're going to a space at least of twice the dimension, there's at least one embedding. And the really useful and remarkable part is that once you go to a space of greater than twice the dimension, so once k is 2d plus 1 or larger, in a certain sense, most for mappings are embeddings. Okay, so the topologist word for this is generic or typical. So the embeddings form an open dense set. If you have something which is not an embedding, you can go make an arbitrarily small tweak to it and you will get an embedding, and you can continuously vary an embedding and keep it as an embedding. So you can take just about any function you like, so long as each coordinate is C1 and you're mapping to at least 2d plus 1 dimensions, and you've got a diffeomorphism. It's not exactly the same as almost all because there are issues with defining measures on these function spaces, but it's the sort of nicest topological equivalent you could hope for to almost all. So the typical mapping where each coordinate is C1 also has a differentiable C1 inverse. So how do we use this? Well, we have our nice class of bounded continuous test functions, which generate a nice rich function space. We sample at least 2d plus 1 of those functions. And we're going to assume that there's a limiting expectation value for each one of them. Now we have a mapping from the parameter space to Rk. It's C1 in each coordinate. So we can apply the embedding theorem. We can say, all right, there's going to exist an inverse, and that inverse is also going to be differentiable and continuously differentiable. So as long as we're using at least 2d plus 1 smooth functions of the underlying parameters, we are going to have an inverse between the limiting expectation values of those 2d plus 1 functions and the underlying parameters. So if we just knew those limiting expectation values, there would exist a mapping back to the parameters. We would be identifiable from those parameters, from those expectation values. Obviously, we don't see expectation values. We see actual data, and we can only calculate sample averages, but we can then just try it and see what happens. Okay. So we're going to hope that we have our law of large numbers convergence. So, with increasingly high probability, that should be a convergence and probability arrow. The sample value of one of our functions should be converging on its expectation value. So we would like something like a concentration of measure result. So this holds for a large class of functions all at once, or some sort of large deviation because we're just doing asymptotic statistics. For a lot of processes which have got some nice underlying ergodic properties, we could just do averages of some instantaneous function, or averages over a function of two successive time points along a time series or over a spatial region. Those will have the right kind of convergence as we go to larger and larger sample sizes. So let's just put all the pieces together here for time series. I'm going to say we've got a nice big roomy class of bounded continuous test functions. They have some reasonable ergodic properties, and we have a nice distribution over that. And it turns out that for everything I've looked at for time series, just cosines with a Gaussian distribution over frequencies has worked pretty well. And to slide a window of some length along the time series, we're going to treat each point we're going to as a little vector of some length. So we've got a model with the dimensions. We sample this limited 2D plus 1 functions. We observe our data, and we minimize the gap between the actual functions calculated on the data and the same random functions calculated on the simulations. And if my S key wasn't broken, there would be a factor of 1 over S sum over multiple simulations here. Okay, so we're just adjusting the parameters theta until we have a match between the values of our random functions on the data and the values of those same random functions on the simulation. So I want to show you some examples. I'm going to start with sort of baby's first inference problem, which is the estimating the location of a Gaussian, a univariate IID Gaussian with variance 1. I will then show you the same exact method working for a T distribution. And then I'm going to show you some stuff with dynamical systems where the inference is not nearly so trivial. So, again, IID Gaussians, the only unknown for this simplest possible example is the location. I'm going to fix the variance at 1. Obviously, you don't need to do simulation-based inference here, but this was sort of the first sanity check to make sure that this was not me smoking things I shouldn't mention. Okay, so the or 2D plus 1 is then 3. And so I'm just going to use Fourier one-dimensional univariate Fourier features, meaning I'm going to scan along, I'm going to pick the frequencies at random from a Gaussian. I'm going to pick a phase offset uniformly. And at each point, I'm going to calculate the cosine with that random frequency. I'm going to average it along the time series. I think of it as a time series. It's IID. It doesn't matter. So the first thing to check is, does this actually let us identify the parameter? Right? Is there enough information here to identify the parameter, whether or not we can estimate? And so what I've done here is I'm showing you the sample values of my 3 random Fourier features. As I vary the location parameter from a very negative value in blue to a very positive value in pale tan. And I've done this for 2 realizations of the random noise, and this is only a sample size of 100. So you can see that, yes, as you vary the parameter, you get different values of these features. Yes, there is a one-to-one mapping between the features and the value of the parameter. Yes, it is smoothly invertible. So if you're a little bit off in the features, you're only going to be a little bit off in the value of the parameter. not making a huge difference. But if we averaged over multiple realizations, we would get something which was even more. So we've got the stability we want. We have the invertibility. This is sort of showing that it should, in principle, be possible to invert this and get a parameter estimate. And here, distribution of those parameter estimates. So I am saying I want to adjust the location in my Gaussian simulator until I match the values of those 3 random features. The black line is the smoothed, kernel smoothed density of the estimates from my method. The dotted line is what you would get from the MLE. I want to emphasize this is just one totally random choice of those 3 features. I did not run this many times until the figure came out looking good. So it's admittedly at a reasonably large sample size of 1,000. Okay. You can then ask, okay, what is the mean squared error of estimating the location parameter in this way by matching random features as you increase the sample size? The dark line is showing that for this random feature method. The gray line is what is the exact mean squared error of using the maximum likelihood estimator here, because of course, in this situation, you can work that out. In this situation, for 3 features, we are getting about the same error, about the same accuracy as we would get from the MLE, which is efficient here. I don't claim this is always going to happen, but at least in this situation, it's working quite efficiently. The relative efficiency seems to be pretty close to 1. So that is with the, as I said, the absolute simplest inference problem you could imagine. Let's do something just a little bit more complicated, which is again estimating a location parameter, but now instead of the location being a Gaussian, it will say it's a T distribution. So I picked a T with 5 degrees of freedom. It's heavy-tailed. Any moment above the 5th doesn't exist, but it's still just a one location, a one parameter family. So in the for the Gaussian, I made up 3 random Fourier features. I'm now going to use the same 3 random Fourier features that I did for the Gaussian for the T distribution. You could imagine trying to work out the MLE here. There is a likelihood function after all. It would be a pain. Like a sensible person, I'm going to just do that numerically. So what we're seeing here, again, in black is what is the MSE from estimating this location of the T distribution using those exact same 3 random Fourier features. And the gray line is the numerical MLE. So the mean squared error is pretty comparable and has the same scaling as we increase the sample size. And what I want to emphasize here is I didn't have to think at all about the difference between the Gaussian distribution and the T distribution. I didn't even have to think about the fact that I was estimating a location parameter. I just had to know I was estimating a one-dimensional parameter, and that I was using my sample space was, as it happens, also one-dimensional. So those are some sort of easy things. I want to show a harder one. I realize I'm running short on time, but I think I have enough to go through this. So this is a deterministic nonlinear dynamical system, which gets called the Logistic Map. And the way this goes is there's some initial value, which is I'm going to make it uniformly distributed between 0 and 1. And then once the initial value is chosen, all subsequent values are generated deterministically and recursively. There should be a t+1 over here. Sorry about that. So the next value comes from plugging the previous value into just this quadratic. 4 times r is a parameter times xt times 1 minus x of t. So it starts around 0, it reaches up to some maximum and what half, and then it arcs back down towards 0. R, for very small values of R, it goes to a fixed point. For larger values of R, it goes to some periodic cycle. For very large values of R, it goes to a chaotic system with a strange attractor, which is actually a fractal. Okay. For large enough R, this has chaos or sensitive dependence on initial conditions. And in particular, I'm going to show some simulations where R is 0.9, which is fully chaotic. So the output of this looks, if you just apply standard tests, very much like a stochastic process. There is an underlying determinism, but very small errors in the initial value, differences in the initial value of X get amplified exponentially. Now, you could, in principle, try and work out the parameter R by maximum likelihood, because it's a deterministic system. If you can measure numbers to infinite precision, just seeing X of t and X of t plus 1 will tell you R exactly. Any particular trajectory is either certain or impossible. But that's not a useful way of trying to work this out with any kind of finite precision. Likelihood is just not very useful here, so I won't show likelihood results as a foil or baseline. But what I am going to point out is I've got a known parameter here. So D is 1. I should be able to use 3 features. So I took the same 3 random Fourier features that I built for the Gaussian, and I said, I'm just going to apply that along the time series of this dynamical system. And when R is very small, you get values up here. And as R increases, you move along this slightly kinked, but still smooth one-dimensional curve. So I'm showing here the results of averaging 10 trajectories per parameter value. The trajectories are only of length 100, so it's fairly short. But this is saying, as I vary the parameter and I look at the expected values, or really approximate expected values for these 3 randomly chosen features, I trace out a one-dimensional curve, a smooth one-dimensional curve. And if I'm a little bit off about where I am on that curve, that translates back into being a little bit off in the parameter value. So this is the distribution of estimates of that parameter R, where I'm taking those 3 univariate features I originally built for the Gaussian. And again, I'm running 10 simulations per parameter value, and I am minimizing the distance in those features. And that little tick mark below the axis is the true parameter value, which is 0.9. And so the sensible range for R is just the unit interval 0 to 1. With only 100 time steps, it's doing very nicely at coming up with very accurate estimates of this underlying parameter. And I will not show the figures, but if you change the underlying parameter, if you make it 0.65, where it's periodic, it estimates about 0.65. What I will show is that if you increase the sample size so that you go from using a time series of length 100 to time series of length 1000, with length 100, you're seeing these dotted lines. And I've done a couple of different variants on how exactly we do the minimization, which you can read about in the paper. They don't seem to make a huge amount of difference. But with the dotted lines, you get this distribution between, at sample size 100, between about 0.89 and 0.91. If I increase the sample size, we would like to see this getting more and more concentrated around the true parameter value. And indeed, the densities for a sample size 1000 are much more concentrated around the true parameter value. Again, more or less very similar across different slight variations in how exactly we do the minimization. So it's giving us apparently consistent estimates of a nonlinear dynamical system without knowing anything about the underlying nature of the model. These are, again, the same random features I used for estimating the location of the Gaussian. And just as a final example, because then I think I'm going to be out of time. Same dynamical system, same underlying dynamical system, and I'm just going to observe it through noise. So instead of so now this S variable, which I'm not going to directly observe, is going to follow the logistic map, and I'm going to observe the logistic map plus a certain amount of noise, Gaussian noise. So now I have two parameters. Finally, a multi-parameter example. Because I've got two parameters, I would need 5 random features. I tried it with 5 random features. I've got 2 parameters to estimate. And what you see here is how well can I estimate the R parameter, the one in, missing here in the underlying dynamics. Again, as we make the sample size larger, we get more and more concentrated estimates over multiple ways of doing the minimization. But we can also correctly estimate the noise parameter, the noise amplitude parameter at the same time, the noise variance. And we get more and more concentrated estimates as we look at larger and larger data sets. So what do these examples tell us? I started with some really easy problems where I can work out what would the maximum likelihood estimate be, and I know that MLE is efficient. Matching the minimum number of random features seems to be pretty competitive there. I do not have anything remotely like a proof that it should be in general. It would be wonderful but surprising if it was, but there are at least some problems where it is competitive with the MLE. If we take these much more challenging problems about dynamical systems where everything is interdependent and there are very strong dependencies, at least over short time periods, and long run, it's very impossible to predict anything, it's at least working. It's at least giving us estimates which are converging on the true parameter values without any kind of fine tuning or any need to think about what is the nature of the model at all. The same random features that worked for those trivial location family problems are also working for these more complicated dynamical system problems. So what is the agenda? The first question as a theorist I wanted to know about is efficiency. I'm quite confident that 2D plus 1 random features are going to be enough for identification, for consistency, but I would be astonished if they are usually efficient. It would be very nice if there is some way of saying, with this distribution of random features, the asymptotic relative efficiency will be blah, 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 for long formula follows. And it would also be nice to know if we use more than the minimum number of random features, can we get closer and closer to an efficient estimate? I strongly suspect that last part is true, but again, I don't know it. For time series problems, I said, we can just treat it as univariate, treat it as just a histogram essentially, and calculate random Fourier features on that, or we could do a bivariate histogram and calculate random Fourier features on that, and that some of the different plots, different lines in those plots. It's not clear when we're going to get more information from longer blocks. There's no reason to stop at bivariate. You could do 5, blocks of length 5 and calculate Fourier transforms of that. You might expect that if there are long-range dependencies, you might get more information from looking at longer blocks. It would be nice to know if that's true and at what rate, how big the block you can get away with if you're looking at a limited length time series. So those are sort of technical futsy things where I'm sure somebody who is smarter and better at calculus than I am can do some interesting work. The two things where I'm really not sure how to approach, but I am hopeful that there will be something, and we'll be able, there'll be some progress to report in 6 months or a year. One is about what to do with non-stationary processes, because there does need to be some kind of convergence between of these features calculated on a single random realization and expectation values. And if expectation values are themselves changing because the process is really non-stationary, it's not clear to me exactly what we should be doing there, or what kinds of features would play nicely with underlying non-stationarities. So I have a couple of ideas, and I'm hoping that I'll be able to tell you something about that in a year. The other thing where I really don't know what to do, but I hope that we'll be able to do something, is all the examples I've tried so far are time series or spatial data on regular grids. And we're talking a lot of research time is spent thinking about networks to networks. If the data itself is a random graph from some distribution, model which generates graphs as your outcome of interest, what is the right equivalent of random frequency cosines for networks? And I honestly have no idea, but I presume that, and it might even be computationally tractable. All right, I am out of time. I want to reiterate the things you should take away. So if you have a generative model, a simulatable model, it forms a nice d-dimensional parameter, a d-dimensional manifold for the parameter space. You should be able to just use 2D plus 1 random basis functions. Matching those should generally let you identify the parameters. If you have consistent parameter estimates by matching those parameter values, those expectation values. And the thing which makes this nice is that you don't have to actually understand much about the model to make this work. You need to know something about the sample space, but if you have the same kind of sample space, you can reuse the same sort of random features across many models and still get consistent estimates. And in some cases still get efficient estimates. I very much hope I encourage people to think about how you could apply this, and especially how we could extend this to situations where it's not so clear what the good basis functions are, and what to do about really non-stationary processes where transients or long-run trends are very important. But it'd be not play nicely with the ergodicity we want for convergence. So in conclusion, I want to end in meme form, which is to say there is a tension here between my superego as a statistician, which is that it is very important to understand the model and everything that's going into it, and my id as somebody who is now very proud of this brainstorm, which is that we just need to throw more random sine waves at it, and if you can match those Fourier basis functions, we're good. That is all. Thank you very much for your attention. I apologize for going into negative time by 2 minutes.
Thank you, Cosma. And